Hello everyone, I will be presenting a responsive knapsack based algorithm for research provisioning and scheduling of scientific workflows in the cloud. What is this paper about? Let's look at the abstract. Scientific workflows are used to process vast amounts of data. We all know that the world is going towards data-driven solutions, and to process this data we have a lot of workflows. And we also know that these workflows are really time consuming and they run on distributed platforms. So what we're saying is scientific workflows can actually utilize the ease of access, affordability and scalability that is offered by cloud computing. Cloud computing is nothing but a service that is offered to organizations where you pay on use on demand basis, and you basically save your data on the cloud and retrieve it when you require it. This paper proposes an algorithm to address the challenges that are faced when you use cloud computing. The introduction. Workflows are basically a set of computational tasks and set of data or control dependencies between them. So suppose you say that you have a particular task. To execute this task, we have workflows. So that is what it says. Scheduling algorithms play a crucial role in running workflows efficiently. So for the workflows to be executed efficiently, there are scheduling algorithms which say which workflow should run before which one and which machine should execute which workflow. That's what they mean by scheduling algorithms. These scheduling algorithms should consider three key factors: on-demand elastic resource model, utility-based pricing model, and dynamic state of cloud, which leads to uncertainties. So to meet the above mentioned three factors, a workflow responsive resource provisioning and scheduling algorithm has been proposed as a solution in this paper. What is the aim of this WRPS algorithm? The aim is to minimize the overall cost of utilized infrastructure. That is, like I said, cloud computing is pay on use basis. So you want to reduce the cost you spend, which means you utilize the cloud services or the infrastructure wisely. Now, deciding which computing resource to use given the heterogeneous nature of the virtual machine is another important characteristic WRPS algorithm is supposed to have. What do they mean by a heterogeneous nature? We all know that virtual machines are not real computers, but they are virtual computers which have CPUs. Suppose we consider two virtual machines with the same configurations. There might be times where one virtual machine can outperform the other one due to various reasons, one of which can be an unexpected delay that could occur. So to meet these natures, the algorithm should be able to So due to this nature, the algorithm should be able to compute resources, and the experiment results show that WRPS algorithm is scalable, robust and responsive, and it also generates better quality solutions than the state-of-the-art algorithms. We know that there are a few existing algorithms already. Some of them are dynamic and some of them are static. An example of a dynamic would be dynamic provisioning, dynamic scheduling algorithm, but it has a disadvantage, which is the task level optimization strategy. And an example of a static algorithm would be static provisioning, static scheduling. This algorithm is very sensitive to execution delays and runtime estimations of tasks. So we need to find a bridge between dynamic and static, and that's where WRPS comes. The WRPS algorithm basically combines both the dynamic and static features to balance between adaptability and optimization. I'll give you some background before we jump into the details. I said that I mentioned workflow quite a lot of times. So what is this workflow? Workflows are considered to be modeled as directed acyclic graphs. A workflow is composed of a set of tasks and edges. Then the size of task is measured in millions of instructions. Excuse me. So when we say tasks, it's nothing but task 1, task 2, task 3, and edges are nothing but, let's just consider edge I to j. That is an edge if there is data between I and j. And virtual machines are leased on demand and charged per billing period, as I said before. Virtual machines are modeled in terms of processing capacity and cost per billing period. This is nothing but a virtual machine is designed in a way where you can see the capacity, that is how much it can process, and cost, how much it costs for a period. And also this WRPS algorithm uses a global shared storage as a file repository. Instead of taking the output from one task and giving it as the input to the next task across the networks, it is easier to use a file repository. I'll just give you a brief description of the WRPS algorithm so that you'll have an idea before I get into the details of each of this. WRPS has both dynamic and static features as mentioned earlier, and scheduling decisions are made at runtime, which allows it to adapt to unexpected delays and environment changes. This is where the dynamic feature comes in. So suppose it assumes that each task will take a certain amount of time and it schedules it accordingly, but during runtime, due to some reason, there is a delay in one of the tasks completion. Then this algorithm is able to change the schedule of the other task in a way to meet the deadline. It expands decision making ability from a single task to a group of tasks, and it implements the concepts of pipeline. This is where the static feature comes into picture. The group tasks of the same type and same deadlines are put into a bag. What is a pipeline? A pipeline is a group of tasks with a one-to-one sequential relationship between them. Let's see the details of a pipeline. Like I said, pipeline is a group of tasks with a one-to-one sequential relationship. Let's consider the equation. It says that there are tasks T1, T2 up to Tn. So basically here T1 is a parent task of T2 and T2 is a parent task of T3. The first task in the pipeline can have more than one parent but should have only one child. So basically it says first task should have one child and can have many parents, but all the other tasks should have one parent and one child. Excuse me. Pipeline is associated with a deadline which is equal to the deadline of the last task in the sequence. Tasks in a pipeline are clustered together and assigned to run on the same VM. So they are saying tasks should be clustered together to avoid processing overheads, and the tasks always run on the same virtual machine because the tasks are sequential, so they can run one after the other. Output of one task becomes the input to the next task, which will avoid the cost of time transferring files in and out of the global storage by running on the same virtual machine. Before we go ahead with I wanted to explain to you what the knapsack problem is, because the WRPS algorithm uses the knapsack concept. As you can see in the picture, there is a knapsack in between and it can hold a weight of 15 kgs. Our aim is to add blocks into the bag such that we get maximum value and at the same time we meet the weight requirements of the bag. So in this example that we can see, we have the green block which is 12 kgs, but the value is only just $4, whereas we have the yellow block which is value of 10 kgs and it weighs only 4 kgs. So we definitely want to add that to the bag, and obviously we can't add the 12 kg now. The other three blocks are just 1 and 2 kgs each, so we can add that. By this we have maximum value which is $15, and the weight is just 8 kgs. Now let's take a look at the algorithm of WRPS. This is what the algorithm is. What's happening here is the WRPS first pre-processes the DAG by identifying the pipeline and assigning a portion of the deadline to each task. The tasks are then sorted. For each sorted task that has not been processed, the algorithm recursively tries to build a pipeline that starts with that particular task. When processed task has only one child and one parent, it is added to the pipeline and the recursion continues with its child task. Once the pipeline is identified and recursion completes, the process is repeated for the next unprocessed sorted task. These are a few terms which are worth noting. Deadline distribution. The algorithm first calculates earliest finish time of all the tasks and the slowest excuse me, and the slowest time is used to calculate the task processing time. Spare time is calculated and divided between the workflow levels. Spare time is nothing but the difference between the deadline and the earliest finish time of the workflow. After these two, finally the deadline is assigned, which is nothing but a combination of the finish time and the spare time. This is how the WRPS works. The DAG is first pre-processed and task schedule begins. Tasks are grouped into bags of tasks and bags of pipeline. Bags of tasks are one or more tasks that can run in parallel. Bags of pipelines are one or more pipelines that can run in parallel. The difference is the tasks in the bag of tasks have same deadline, whereas the bag of pipelines have different deadlines. The WRPS assigns as many tasks as possible to the already leased virtual machines. Obviously, we do not want to lease more virtual machines which will incur higher cost. Therefore, it tries to assign tasks to the machines that have already been leased. And how does it assign tasks? It depends on how many tasks a virtual machine can process and complete by the deadline. If we consider an example where there is a bag with single task, the single task is scheduled on a free virtual machine if the finish on time and before the billing period. If there is no virtual machine existing, then a new one is created. The WRPS continuously adjusts its deadline distribution to reflect actual finish time. If a task finishes earlier than expected, all the other tasks have more time to run and therefore cost can be reduced. So suppose you have two bags with two single tasks and you consider this virtual machine can execute one of them, and suppose it completes before the deadline and the remaining time is enough for the next task to run, then without having to lease another virtual machine, you can use the existing virtual machine. Also, if a task exceeds the deadlines, then all the other tasks are updated to avoid delays, therefore enables adaptability to unexpected delays. Suppose that there is some task that's taking more than expected time, then the tasks are updated so that it can be adapted to those unexpected delays and probably rescheduled again. The WRPS algorithm has been experimented, like we said, and the results are evaluated using 4 well-known workflows: montage, epigenomic, LIGO, SI-PhD. By comparing these with WRPS, the solution can be validated to show how the WRPS algorithm is successful in cases where the other four workflows are it is successful when the other algorithms fail to recover. So one of the most important factors to consider during evaluation is make span and cost evaluation. Just for you to understand, the left side is the make span and the right side of the diagrams are the cost graphs. The first row is for LIGO, the second for Montage, third for epigenomics, and the last one is for SI-PhD. The reference lines are the four deadlines values for each workflow, which is found on top of all the make span charts. It is important to evaluate the make span, and because it is the main objective, one of the main objectives rather, to execute a task before the deadline. And cost chart is also important because it is another main objective where we should meet the deadlines, and also the system should be cost efficient. Let's consider each of the workflows. For LIGO, the deadline 1 is too tight, but the deadline 2 is not too bad. WRPS successfully completes the execution before the deadline, but we can see that the other three still do not succeed in completing before the deadline. We also note that WRPS is very cost efficient. Therefore, we can conclude that WRPS outperforms in terms of execution cost. For Montage, SES and WRPS meet all deadlines. However, WRPS constantly generates cheaper schedules. So therefore, WRPS is considered better than SES. For epigenomics, all the three algorithms fail to meet the first deadline, but in the second deadline, WRPS is again successful with very low execution cost. And SI-PhD, this is actually a very interesting application because of its topological feature. Even in this case, WRPS remains responsive, as we can see, and it also meets the deadlines with the lowest make span and the lowest cost. So what can we conclude from the above charts and cost charts and make spans we just saw? We can conclude that WRPS is most successful algorithm in meeting deadlines. It is also highly efficient when it comes to generating low cost solutions, and WRPS constantly increases its time for execution as the time for deadline is relaxed. Since many users are willing to compromise on execution time for a lower cost, this comes in handy. Another important factor to consider while evaluating the performance of this algorithm is the network usage evaluation. We know that network links are bottlenecks in the cloud environment, and therefore it is important to schedule algorithms to try to reduce the amount of data transferred through the cloud network infrastructure. The bar charts here show the average number of files and the average number of files that are read across the 4 deadlines for each workflow and algorithm. By scheduling pipelines in a single virtual machine and running as many tasks or pipelines from the same bag in a single virtual machine, WRPS is successful in reducing by 50%. The files read from the storage are reduced by 58% in the case of LIGO, 75% in the case of epigenomic, and for Montage it reduces approximately 50%. Having done and said this, what is the future work that can be done? Is the WRPS algorithm perfect as it is? Not really. Why? Let's look at it. So the WRPS is not very successful in reducing the number of files in SIPHT application. As we saw, it doesn't reduce the files very much, and this is mainly because of pipelines and bags of tasks not being present in SIPHT. This is one of the main drawbacks. So a future work could probably include coming up or developing a new heuristic so that the WRPS is capable of scheduling these types of workflows more efficiently than just being at the margin. Conclusion. This paper presents a WRPS algorithm for scientific workflows in cloud. It minimizes the overall cost of cloud while meeting user-defined deadlines. The algorithm is also dynamic to respond to unexpected delays. It is static and can find the optimal schedule for a group of workflow tasks. And also we saw that the simulation results show WRPS has better performance than the state-of-art algorithms and also achieves this at low cost. It's nothing but by reducing the workflow into bags of homogeneous tasks and pipelines that share a deadline, we are able to model their scheduling as a variation. The unknown knapsack problem and solve in pseudo-polynomial time using dynamic programming is another thing that the WRPS does. And that's it. Thank you. Hope you guys liked it.